No, I'm super delighted to be here. I thank the organizers for the invitation to present what is a really broad topic and could easily fill an entire school of lectures. So obviously I'm going to have to pick and choose topics as I go, and that will have its own consequence. Some of you will like the topics that I pick, or some may like any given topic and not like the next topic. That's just maybe how it goes. But okay, hopefully my main goal here is not so much to talk about in detail specific models and specific things, even though I will end up doing that a little bit, but it's more to try to illustrate the principles that sort of BSM theorists use to go and think about physics beyond the standard model principles, obviously beyond just sort of standard quantum field theory that you already know. Yeah, so we'll see how it goes. I'll give you an outline in just a second. I do want to just also make just a couple of comments that also echo what Igor has said this morning. It was a really tragic loss to have both Steve Gupser and Nelson die, both in one in a climbing accident and one in a mountaineering accident. As a climber and a mountaineer, of course, that hits me to the core as well, because when I'm not doing physics, I like to be out in the mountains, and and certainly both of them were of that variety as well. I will say, Anne has had a huge impact on, beyond the standard model physics. So many different areas, from supersymmetry to electroweak baryogenesis, little Higgs theories, compositeness, and so forth. It's hard to imagine areas she didn't actually touch, and so to be giving sort of these lectures, sort of following that is anyway, it's a great privilege, and hopefully. All of her, hopefully, she will live on in all of the great physics that she did, and that has now sort of been infused into all of us. Okay, all right. So, okay, with that, let me begin. Physics beyond the standard model. And the cry you just heard is often the cry I sometimes hear, because you get people who will say, in fact, I was just meeting a colleague not that long ago, and I told him I was giving physics beyond the standard model lecture. He said, oh yeah, well that'll be quick, it'll be 30 minutes and it's over. Okay, and no, it's not going to be 30 minutes. It won't be over in 30, so yeah, you're going to be here. And in fact, I will say one more thing, which is I'm giving 4 lectures over 4 days, as you know from the schedule. I'm the only one giving lectures on Friday, so that frees me to some unique opportunities for what I could be doing on Friday. And so for those of you who actually stick around all the way to Friday, then maybe we'll have some even more fun by then. Okay. So in the meantime, I have to be a little bit more, pedantic, so that I don't offend people. Okay. But the first obvious question would be why? Right? Why do we want to go beyond? And well, there is physics. There is physics beyond the standard model. There's dark matter and neutrino masses. Mixings. And I should also say, my handwriting sucks. I'm aware of it. I can read it, but that doesn't help you. So if there is something that you just ask. Don't hesitate. Don't let the writing stop you from saying something. So these things need physics beyond the standard model, and of course. One of them is a huge subject, and we are going to get to that. Okay, but that's not going to be the first subject. It won't be the subject of today, but we'll talk more about dark matter in a little bit, and probably starting lecture 3. Neutrino masses and mixings. Some of you may think, depending on your point of view, is wait, we've had this for a while. Isn't this just part of the standard model? Okay, so one of the goals, or one of the little goals I want to do right today, is to explain, no, that's wrong. Neutrino masses are physics beyond the standard model, and I want to explain exactly what that means, because that allows me to define what is the standard model and what it means to go beyond. Okay. That's not the only reason to do physics beyond the standard model. And maybe the next obvious reason to do it is to have some sort of consistent, whatever that means, parametrization of new, and I really have in mind here, heavy physics. Okay. So this usually goes under the name of, say, SMEFT, Standard Model Effective Field Theory. And well, you can certainly, and we do, treat the standard models in effective field theory. You know, all of the theories we work with are effective field theories, at least in particle physics. And so the notion that we treat the standard models in effective theory is no surprise, and this is obviously one of the crucial things to sort of gain and really sort of, you know, acquire the, well, I don't know how to say this exactly, to sort of absorb and become comfortable with that this is how we should really treat it. But by that, of course, I'm going to have to define a little bit about what I mean by these two things. But the other reason, of course, to have a consistent parameterization is if, after all, you didn't have this, then experiments of all different varieties, from LHC to, you know, fixed target experiments to all sorts of precision experiments, at some level there'd be no point in doing them because we've already measured virtually all of the standard model parameters anyway to a reasonably good accuracy. So what's the point in going further? So unless you're going to improve the accuracy, then why would you keep on doing these searches? So this, though, is precisely what allows you to consistently parameterize what those new physics contributions would be. What else? Okay, there are obviously, so I'm sort of, you know, I'm going in a particular, well, I'm going in an order which is not necessarily the order you may or may not have thought of, but these are certainly all reasons that you want to do it. There are other reasons that we also would like to think, and they really just boil down to aspects of naturalness. And for a long time, this was sort of, I would say this was sort of, you know, gospel or religion, okay, naturalness, it's there, okay. Well, at some level, parts of this are still absolutely and have not changed, all right? The issues of naturalness and how we understand things, parts of this have not changed. Some parts seem to be in tension with experiment. So we have to understand that, and, you know, so obviously you know the problems that come in here. There's everything from the cosmological constant problem to the usual, what I will call the hierarchy problem, problem, puzzle, pick your favorite word. So by this I mean mh squared, theta QCD. Right. And so a reason to do this is to attempt to, you know, make some headway with one or more of these problems. I'm not going to talk about the CC for the whole lectures. So.
What's the last thing?
Theta QCD.
Okay.
Yeah. Strong CP.
And doesn't the cosmological constant problem has to do with the hierarchy problem?
That's a great question. It's a great question. Maybe it does, maybe it doesn't. In a little bit, today or tomorrow, I can't remember the ordering of the lectures, but I will at least give you a rationale for not necessarily. Okay.
Okay.
Yeah. So I'm not going to talk about this and then, okay, go from here. There's other things you could do, and now I'm getting a little bit more historical, but that's okay. You know, we have this wonderful standard model of 3 generations of quarks and leptons with all of their crazy mass parameters, and you could imagine that somehow there is a way to explain or rationalize or justify, I don't know, let's call it explain, let's be optimistic. So fermion masses and mixings. Also, for a long time, people thought that 3 gauge groups with all these crazy quantum numbers would be something else, something bigger, something grander, right? Okay, so GUTS, grand unified theories. Again, this is sort of historical, different things people did to go beyond. Of course, also baryogenesis, which Genesis / lepto. But fortunately, I don't have to talk about that. So Misha's doing a great job. Okay, and I think maybe in the end, you could just sort of say, well, think imaginatively. So what can you possibly do that you could then potentially see, right? So rarely do we think imaginatively completely uncoupled from the rest of what we do, but sometimes you do, right? Sometimes you may think about things that have absolutely nothing to do with the standard model, okay? And that's okay if that sort of allows you to try to understand principles, okay, of how to go. All right. So, as I said, the focus is going to be sort of try to be on the structure and sort of things that I think are interesting to sort of glean from what people have been doing in BSM physics. And I necessarily have to pick out sort of isolated topics. I'm not going to be able to cover everything, it's just not possible. All right. Well, let's get to the first one that I want to do today, which is neutrinos. Masses and mixings. So, I'm not a US government lab employee, so it's not like I'm required to say this, by the way, despite all of the money and effort that's being poured into neutrino physics in the US. Nevertheless, I think it's a good sort of first place to begin the conversation about what is the standard model, what is beyond the standard model. So, the standard model, 3 generations of chiral quarks that I'm free to put all into a left-handed representation, right, and then proceed. We have a Higgs sector that contains the 3 goldstones that get absorbed by the W and the Z, as well as the scalar excitation around the minimum, our famous 125 GeV Higgs boson. And right, this structure, prior to me writing any masses for any of these fields, has a U3 to the 5th global symmetry that is then broken by Yukawa couplings. To U1 baryon number cross something to do with lepton number. Let me get to that, okay? Okay, so baryon number we know, it's a good classical symmetry for the standard model. Of course, it's broken by non-perturbative effects, as we're going to hear more about, or maybe already heard, okay, with regard to baryogenesis. But for this purposes, it's effectively exact. Okay. Then from this content, we just write a Lagrangian and construct all of the operators that are allowed by the symmetries, which I could just write schematically this way. And that's the standard model. Usually you write all of these terms, but we don't have to write them all, right? Because we know what the symmetries are. So this, once we know what the SU3 cross SU2 cross SU1 gauge symmetry, these global symmetries broken by Yukawa couplings. So Yukawa couplings that I'm free to add any possible combinations in such a way that the dimensions of these operators is less than 4. Once I do that, bam, that's my standard model. Okay, so that is the standard model, is right. It stops there. And it's just based on on the symmetries of the theory. Once you state that definition, the standard model is this content and it stops at dimension 4, neutrinos are massless. In gross contradiction with experiment. Right. So the observation of neutrino mixings, which then infers the existence of masses, tells us that this is incomplete. Right. This structure that sort of is written very briefly and compactly is incomplete, and we have to extend it in some way. And I'm sure probably most of you are familiar or have certainly heard of the different ways to extend it, but let's just walk through those briefly, because in each case we'll understand something about what it means to extend beyond the standard model.
So why are they massless? You cannot consider a 4-dimensional operator, which is the mass of the neutrino?
Sorry, one more time, just ask the question.
So why are they massless? Can you consider them 5/5?
So the neutrino is buried inside the lepton here, and so maybe okay. Let's just elaborate slightly more. So if I actually write out the Yukawa couplings, I have U, Q, H. I can't remember if it's epsilon or not, but that's fine. U plus D, I, J, Q, J, H. One of these is daggered. I'm going to guess D and Y, E, L, H, E, conjugate, IJ. That's with this field content of QUDLE, I am free to write interactions with the Higgs, but only these combinations. So this gives all of the up quarks mass, this gives the down quark masses, this gives the charged lepton masses, but that's it. With this content restricted to here. Okay. So obviously a trivial way to extend this would be to say, well, okay, following down this trend, let's do that. Add this thing in, and then suddenly I have Dirac masses. Because now I can write the coupling that maybe you were hoping for, or maybe not, I don't know. Always be careful about understanding what other people's hopes are. There we go. And if I just slightly do a slight abuse of the what the data is telling us, here I've nominally extended this to 3 neutrinos. Right. Okay. The data, of course, tells us two mass differences. That's what we know for sure. So one of them could in principle be massless. That's also fine. That would just be encoded in there being a 0 in the mass matrix, okay. Or in the Yukawa coupling that would lead to a 0 in the mass matrix. So, good, right? So this is an extension of the standard model simply because you have extended beyond the QUDLE structure. You said, I have a new field, and not only is it new, but it's light, right? It's when a light field, this thing is married off with the left-handed neutrinos, getting masses of something of the order of, 10 to the minus 1 or 2 eV, right? The mass differences are of that order squared, so the masses are something of that size. Okay, so what we would end up here is that after I give the Higgs an expectation value, I get Y nu V, which is the mass of the neutrino, whatever numbers it needs to be, something like 10, well, let's just write it as 10 to the minus 1 to 10 to the minus 2 eV, or so. Twiddle, there we go. All right, now I'm good. So from this, of course, we can deduce what the Yukawa is. That's nice. That's wonderfully trivial. And if I did it right, it's something like 10 to the minus 12 to 10 to the minus 13, depending on exactly what you put in for V. Okay. Yeah. And at this point, you could say, well, wait a second, that's crazy. What are you doing to rack masses with 10 to the minus 12 Yukawa couplings? No, there's nothing wrong with that. It's perfectly reasonable. This could be exactly how nature is. Could be. We don't know yet, but it could be. You might say, well, 10 to the minus 12 to 13, that's crazy. How could you have such a small number? We already have those small numbers. We already have Y electron, which is at 10 to the minus 6, or Y muon, 10 to the minus 4. So what's the big difference between 10 to the minus 6 and 10 to the minus 12? Really? I mean, it's just, it's not that big a difference, right? If I'm already got a 10 to the minus 6 number, I'm certainly going to be happy with a 10 to the minus 12 number. Okay. So this is at least one possibility for what it means to have neutrino masses. So, right, it means there is an additional field, an additional Weyl fermion, presumably 3, doing again a little bit of an abuse of the data, okay, but presumably 3, but not necessarily 3, at least 2 Weyl fermions that then marry off with the left-handed neutrino, just like the quarks and the charged leptons do, and then they have these tiny Yukawas.
Lagrangian, or if you can write the term that respects all of the symmetry of the Lagrangian, then you have to write that term. Yeah,
that's what that's what all of our model building fathers and grandfathers taught us, right? Yeah, right. That anything that is not absolutely forbidden is required,
so
right?
You have to continue that Yukawa with another M nu, right? Isn't it a Majorana term? So it's a complete singlet of the standard model. So don't you necessarily have M nu as well?
So
unless it's buried in the lepton number.
Right. So you've put your finger on precisely the next statement I was going to make, which is great. Nope, that's great. Which is the other property of this is that it preserves lepton number. So in a sense, right, in the way in which that I would have said baryon number is conserved here, then this, right, I conserve lepton number, and then I don't have that possibility. Right, okay. So, all right. Now, at this point, of course, I think, right, these are small numbers. These are small numbers. But we don't, model builders, beyond the standard, all of us, but especially BSM theorists, we have no problem with any of these numbers because of the famous notion that they satisfy, which is URAL. Technical naturalist, right? Back to Tufte. Right, and technical naturalness tells us that if we send a parameter the Lagrangian to 0, and we enhance the symmetry, then it's technically natural, and these parameters basically will stay of the size that they are. Diagrammatically, we can just do that. So I can pick whatever my favorite fermion is here, and I'll use sort of this notation where the mass flips the chirality or flips the arrows of the lines. And then, so this, whatever the sort of, the effective mass of the, or the radiatively corrected mass of the neutrino is, would be whatever I started with a Higgs, YV, and then further corrections. Okay, so this, oh yeah, and of course, in many instances, I'm forgetting things like that are obviously there when you need them. Okay. Whatever, so if this is a gauge coupling, then maybe I have a G squared here, okay. And then there's some, there's some numerical calculation I have to do to get the answer. But the key thing to all of this is that I get a structure that looks like this. Some number, maybe a log of scales. So the neutrino Dirac Yukawa is multiplicatively renormalized. Oh, I'm running out here. Renormalized. So that keeps it small. So that's why we don't immediately get concerned with small electron masses, small muon masses, or for that matter, if it happened to be Dirac neutrino masses, very small Dirac neutrino masses. Okay.
But I'm not understanding the argument. So what happens if there's a small number?
So small numbers some small numbers are multiplicatively renormalized. So if you set them small, they stay small. Other small numbers, or small relative to something, you set them to some value and they renormalize to some very different value. I'll show you, obviously we're going to talk about both the Higgs mass squared, the hierarchy problem, where that's the famous one, but I'm actually also going to tell you about another technically unnatural coupling that is order 1, but whose technical unnaturalness has fundamental consequences for the nature of our universe. Okay, we're getting there. So just bear with me. Yeah. Now at this point you might think, I've got him, because I stare at this diagram and no problem. I can find a diagram that will hit the other Yukawa. I can just, this is if I can just find an eraser, I could do it. There we go. This is going to be fun. We can do f. Use a W loop to some f prime conjugate. And then I go back to this, right? Great. So now I'm hitting a different Yukawa, right? I'm hitting not the original one, not the term that would have linked f with f conjugate, but instead it's, say, it's W partner. And as we know, right, the up quarks and the down quarks have different masses. So suddenly, if I imagine there was a big difference, say like the top quark to the bottom quark, it would seemingly violate that. What did I do wrong? Or is this actually there? Yeah, they're on shell. Yeah, okay, yeah. Sorry, I'm not. Yeah. So, yep. Okay. There's something else, though. There's something else. Neutrino. The neutrino doesn't couple to the W. Really? Really? Neutrino doesn't couple to the W. Right-handed neutrino. Ah, yeah. Yeah, that's true. Yeah, there's a small problem here, right? W's famously talk to left-handed fields, not right-handed fields. So this coupling doesn't exist. Right? It's not an accident, right? It's not an accident that this coupling doesn't exist and therefore this isn't there, right? It's all linked into these things that as you send the parameter to 0, right? You restore a symmetry, and so therefore it's technically natural, and you don't get diagrams like this that will disrupt it. At least you don't in the standard model, because the standard model doesn't contain any additional terms. The key thing to this principle here is that there had better be, when we say a parameter is technically natural, you send it to 0 and enhance the symmetry, there had better be only one parameter that breaks that symmetry. Because if there's more than one, well, then all bets are off, right? For example, I could draw almost the same diagram. Almost the same diagram. Here's a fermion. Here's a sfermion. Super partner to the fermion. It flipped its spin from spin 1/2 to spin 1. And in the process, of course, spin had to be conserved, so there is some either Higgsino or Gaugino, right, that flips off the end of this line. Let's say it's a Gaugino for fun. So then I could still follow the chirality if you want. But in the simplest supersymmetric models, this thing is a Majorana mass. The Majorana mass, right, violates this chirality, and then suddenly permits a diagram. Did I do this right? There you go. Permits a diagram that now has a new type of insertion here that's distinct from whatever this Yukawa coupling would be. So what this would be is something where, again, we have, so this is ostensibly a left-handed fermion, right? And then this is a right-handed fermion. Hence, the Higgs being right chiral, couples to the two chiral components together. So this is going to be a left, quote-unquote, left-handed fermion, which has nothing to do with the actual, has nothing to do with the handedness in the sense of the spin. It only has to do with which gauge bosons are allowed to couple to it. So in this case, only W's can couple to this, but then it could flip to a right-handed sfermion and then go off in this way. And all I need to do is to put in some mass mixing between some m tilde squared left-right here into this fermion mass parameter, and suddenly I have a new contribution. Not only do I have a new contribution, but I have one that is independent, ostensibly, of whatever the parameter I started with that was supposed to be technically natural, namely, say, this Yukawa, the neutrino or the quark-Yukawa coupling. Okay. So it's not that something's technically natural and it stays that way no matter what I do to the theory. Obviously, I can break the theory by extending it in some particular way and then adding new contributions that could break it. Right? So you can do that. By the way, of course, this is one part, probably the worst part of what is otherwise known as the supersymmetric flavor And again, no surprise, Ann Nelson played a major role in uncovering the nature of the supersymmetric flavor problem and various solutions to it. So, seems appropriate to mention that here now.
If Z had flavor changing neutral current as well, would that still be like it would kill the technical naturalness of the standard one?
Except that the Z doesn't.
But if it, like, so if you, I don't know, assume another U1 symmetry, so Z gets it, so then.
Good, but you can now you're seeing where you're going with this, which is I add something new and I couple it in some way in which I maybe violate a principle. Yeah, and you can always do that, right? You can, it's it takes effort to keep the car on the road without hitting other cars. It's relatively easy to crash it, right? And it's sort of similar with the standard model, right? It's if you really want to, you can break it pretty quickly, yeah, and this is an example of how that would go. But yeah, it's certainly maybe not. Okay, we can talk about whether Z's are able to do this or not, but there are certainly ways in which you can add new heavy physics that will, completely violate the global symmetries. Okay. All right.
Okay, so
Yep.
how is it solved?
How is it solved? That is, oh my goodness, that's like a lecture. Okay, yeah, I could easily go on and on about that. I spent a long time thinking about this, writing lots of papers about it, for better or worse, given LHC results. Okay, but anyway, okay, I have. So have many other people, and there are any number of possible solutions to this. The generic statement that people will often make. Maybe if I just sort of generalize away from supersymmetry into just new physics in general, you could say, how do I ensure that my new physics avoids having things like this? Some new spurion some new parameter of the theory which, as a consequence of its existence, breaks a global symmetry that was previously broken by, say, just a Yukawa. So a new spurion for global symmetry breaking here, and so what people will often say is that a theory that would not have this type of new interaction would not have additional flavor violation. So people will often talk about flavor preserving theories or minimal flavor violating theories. The distinction there being flavor preserving would have no violations. Flavor violating would have violations only proportional to couplings that you already have in the theory. So if, for example, this thing were in fact proportional to, say, I don't know, YF conjugate, I don't know, something like this, times some scale, then I don't care anymore, because suddenly now I've got a Yukawa coupling sitting in front, and so this multiplicative renormalization is still satisfied. That make sense? Dirac masses. We're done with Dirac. No one really, well, I don't know if anyone really believes in Dirac masses. Okay. Most people imagine neutrinos are Majorana. Which, when I say neutrinos are Majorana, I mean neutrino masses are themselves Majorana masses, which then means what? So it tells me what is the field content in the low energy effective theory. It is just that of a two-component left-handed fermion, but it clearly has some additional components to it, because we already just saw here that if we don't extend the field content, if we don't extend the field content and we restrict to operators less than dimension 4, neutrinos are massless. So I have to violate one of those two assumptions. And Majorana masses are breaking the assumption that the dimensions of the operator are restricted to 4. Of course, the famous case is so-called Weinberg Operator, or otherwise known just as the only dimension 5 interaction in the standard model EFT. So what do I mean by that? So the only dimension 5, restricting to operators of dimension 5, interaction, standard model EFT, consistent with the symmetries of the standard model. And it's just this, LH, up to index contraction, which is certainly not something I'm going to get super concerned with. It's just that. Okay, so I have a left-handed doublet. I pair it with a Higgs. And then this combination, both leptons mean that I satisfy spin. The Higgs satisfies all of the quantum numbers that the lepton has, conveniently. But to be able to do this, of course, I have to go to 4 fields, which is then dimension 5. So it has to be suppressed by scale. Okay. So if you say neutrinos are or have Majorana masses, you are saying the standard model is incomplete. Standard model being, by definition, this with the field content I had before. It's incomplete because I have to add a new dimension 5 interaction. And the dimension 5 interaction has a cutoff scale. A scale at which the theory is no longer valid beyond that point. What do I mean by theory is no longer valid beyond that point? It means the standard model with its gauge symmetries and the field content that it has is no longer applicable to do calculations above this scale. Okay. Once I give, of course, and all right, just to complete this picture though, of course, once I give the Higgs of Ev, all right, that, I don't know why I'm putting root 2's in, but that's fine. Then, of course, I get neutrino masses that go like M nu, okay, in sort of 2-component notation plus Hermitian conjugate, right? Where is, again, up to 2's, and I'm not going to get 2's straight here. M nu is C5 V squared over lambda. Up to 2's, root 2's, whatever. Okay. So you might, well, yeah. This at least is interesting from the perspective that now there is some rationale for why the neutrino masses are in fact so much smaller than electron mass, muon mass, and so forth, because now I have at least a power of V squared over lambda. So if I take lambda sufficiently large, I can get a pretty small M nu. How far can I push this? Well, okay, so you could go to C of order 1 if you like, or maybe a different way to say it would be, yeah, well, okay. So let's just complete the picture, which is that, so if I take C5 that is of order 1, then I find that this scale, this is, as I recall, the lowest scale that will work is about 10 to the 14 GeV. Okay. I could have alternatively just said, you know, lambda over C5 is that. Okay, and that will, this will get me one of the neutrino masses, and the others I can get by just increasing lambda a bit. Okay, so at least by this scale, I had better see something new. So I've gone beyond the standard model because I've added a dimension 5 interaction. Not only that, but I've violated symmetries. Add up lepton number here, right? L, it's the same L. There's 2 of them, and that's it. So this violates lepton number. Although it's a particular kind. It's lepton number violation of delta L equal to 2, right? So, all right. In general, when we try to do, right, any of these extensions to the standard model, or if I maybe just say a few more words about this, since we're on it, right? So what people will usually think about the standard model EFT is they'll write the Lagrangian of the standard model, and then they write a tower of all of the higher dimensional operators. And so maybe let me write them this way. Oh, well, let's erase this. So let me write it as, so there's an O5, which is this one. And then, say, even at dimension 6, then I have a bunch of them here. So this is dimension 6, so it means I construct any possible combinations of the fields allowed by the gauge symmetries, but not the global symmetries that, that I can do in the standard model. And there are obviously many famous interactions that can sit here, right? Everything from, well, yeah, I don't know, famous. Famous is all relative, I guess. Depends on your, what you think is famous. But okay, proton decay sits in here, right? Charged lepton flavor violating interactions sit in there if that's what you want. The S and the T parameter sit in there, right? The electroweak precision, all of the corrections, all of the things that the Higgs measurement, the LEC, ATLAS, and CMS experiments are trying, as they continue, to put more and better precision on Higgs couplings. Ultimately, is boiling down to restricting a class of these operators, right?
And can you consider more dimension 5 operator?
That's it. This is it. There's nothing else you can write. You can try it. It's a good homework exercise. Take the field content, try to construct something. Okay. There's a lot here. $24.99. No, it's not a discount on sale or something. It sounds like it's only $24.99. You can get all the dimension 6 operators. There you go. All right. No, it's 2,499 operators. I didn't do the counting, but people I know who are very good at doing this, including a postdoc who works at Oregon, have done it, and they've done it all the way to dimension 8 or 9. I honestly, I don't remember how far they've gone. And the numbers obviously grow very quickly, okay? Right, they grow very quickly as you go up. This, of course, includes all possible flavor combinations, and that's, of course, where the bulk of this big number is. If I assumed that I had only one generation of quarks and leptons, I would actually be down to only 59, or at least 59 plus Hermitian conjugate. There's always some ambiguity there. So those operators that are not Hermitian, you can add the Hermitian conjugations. Okay. I think this number is 84, but okay, I don't remember now. Still, it's a large number, right? So it means that all of the measurements that we're doing, you can try to map into this sort of thing. Yeah?
Would you then, by that counting, also get 3 for dimension 5 operators because you have 3 versions of the L for each generation?
This is, that's a great question. And what I should have done is written sort of like an I and a J index here and then put similar IJ indices there. And I was just being too quick, yeah. But I didn't actually change the operator. It's still, so it's, yeah, this depends a little bit on how you want to do counting, but this counting, the way this counting is done is that if it's of, good point. So it's 2 here for 1 generation. Fine, all right, you got me on that. Yeah, you're right. Yeah, okay, it's this plus Hermitian conjugate for 1 generation, and then it gets, yeah, fine, okay. Yeah, this stupid indices, all right, fine. All right, you got me on that. Yep. Okay. So neutrinos could be Dirac by extending it with a right-handed neutrino. Neutrinos could be Majorana by introducing a dimension 5 or some set of dimension 5 interactions, but all of the same form of LH up to flavor indices. Okay, LH squared over lambda. The fact that lepton number is violated here and not in the other theory obviously means there's experimental differences. And you can tell. So Delta L equal to 2 means I might be looking for a process that has 2 leptons. And they're leptons, not anti-leptons, which means from a chirality point of view, they have the same chirality. They have arrows that are sort of going out. It's a Majorana mass. Majorana masses are what flip this chirality with this, right, this thing. So here's my neutrino. Here's my neutrino. There's my Majorana mass. Which is, of course, nothing other than really it's this in the notation that I just erased from the board. It's this dimension 5 interaction where I take the Higgs to its VEV. And then this is the left-handed neutrino, right? There's no right on here or anything, right? It's just the left-handed neutrino. Again, why? Because we kept the standard model field content the same. We only extended by adding new interactions. So this is left-handed. Left-handed guy only couples to, famously, W's. And let's complete this arrow thing there. Of course, W's, it's a gauge interaction. Gauge interactions do not violate chirality, so we have, right, incoming, outgoing from the perspective of these arrows. The same here. The Majorana mass violates the chirality, also violates the lepton number by 2 units. So, of course, that's why we write it in this way. Then we have W's. So this would be a way to see 2 different leptons coming out. And maybe all I have to do at this point, if I really want to try to see the process, so you might think, well, that's great. LHC, they do W fusion all the time. They just have, quarks coming in here, quarks coming in there, Q prime, Q prime. Okay, something like that. But after all, this process is going to be proportional to whatever the Majorana mass is. Right. Which is the neutrino mass, sort of. It's the neutrino mass, it's really tiny. So this process is going to be hopeless at the LHC. But we didn't have to go to any arbitrary lepton. We could have gone to electrons. And then if I take these quarks and I sort of embed them inside some big globby thing called a nucleus, then I can have some nucleus. I better check. I never get the N and the Z straight, so just give me a moment here. Here we go. I could have some nucleus of A and Z number goes to some A and Z plus 2, because we lost 2 units in charge if we spit off electrons. So we have to gain in Z number of the nucleus, and then, of course, E minus, which of course is otherwise known as, there's a, I don't know how it's written, but it doesn't matter. Let's just write it. Neutrinoless double beta decay. Okay. So this will happen in the case that neutrinos are Majorana. It won't happen if they're Dirac.
Z plus 2?
Because we lost 2 units in charge of the nucleus. So I'm taking these quarks and embedding them inside nucleons inside a nucleus on this side. And then on this side, these stay part of this nucleus. So it's a nuclear to nuclear transition spitting off 2 electrons. And in that process, if I take 2 units of charge away, I better gain them back somewhere. Because we haven't violated electromagnetism. Symmetries, right? Symmetries always tell you everything you need to know, right?
But how do you know you keep A constant?
So if I didn't, I'd have to emit off other stuff, right? So if A changed, for example, I'd have to emit off if A changed and the nucleus stayed Z plus 2, then I'd have to emit off a neutron. So there'd be another neutron emission from all of this. That make sense? you look up the PDG. It's always the best reference anytime you want to uncover the status of a ongoing experiment or set of experiments and their consequences. So there are various heavy nuclei that are used for this process. I think I didn't even write them down, but you can check the PDG and find out what they all are. The current status is, let's write, yeah, okay. Let's do it this way. Let's, yeah, okay. So let's write here, min, and over here I'll write a quantity that is if there had only been one generation, one neutrino, there would only be one mass that would be here, and then only one thing to go and probe. But in fact, as we know, neutrinos, electron neutrinos oscillate into muon neutrinos and tau neutrinos with highly non-trivial probabilities. Right? Those mixings are order 1, despite the quark masses being mixings that are hierarchical. We don't have any fundamental understanding of that. But for this purpose, what that means is you have to add in the various mixing contributions to determine the effective size of this Majorana mass that would enter for this scaling. So it depends on these quantities. And then what you can do is take all of the neutrino data and then plot it in this picture of the effective Majorana mass that would enter for this process versus the minimum mass that is present for neutrinos. And what you end up with is something along these lines. You get sort of one set of curves that looks like this, one set of curves that, oh, I got color. Let's do this again. Okay. Let's see. Yep. That's close enough. And then there are experimental bounds roughly there. And just to set the scale for everything, this is, let's say this is about 0.1 in EV. This is about 0.001. And this wonderful funnel here, here's 0.01, and this is 0.001, I think. If I got it right, yeah. So what this is trying to tell you is something about the parameter space that neutrinos could live with respect to the effective Majorana mass versus the minimum mass of a neutrino, and comparing that to two different scenarios that neutrinos could take. We have only measured mass differences, not absolute masses of neutrinos. So as a consequence, we don't know whether the hierarchy of neutrino masses follows the hierarchy that we know of the generations. Hierarchy of the generations is first generation's lightest, second generation's middle, third generation's heaviest. With the neutrinos, they're heavily mixed, so there's no way to know which one is supposed to be the heavy one or the light one. And so there's sort of two or three different possibilities. This third possibility of sort of there being quasi-degenerate way up here, that's already excluded by these experiments, so we don't have to talk about that. But then there's sort of two possibilities. There's what's called NH, or normal hierarchy, and, sorry, I got it wrong, sorry. IH, which is the inverted hierarchy, and NH, which is the normal hierarchy. And so one of them, right, one of them puts two neutrinos here and one there, the other one puts two down there and one up there. And I don't remember which one's which. I should, but I don't. So PDG will have it, but this is the point. Okay. So experiments are trying to march down into this territory. How far they get down here will, of course, depend on how well they're able to measure this process. So there's several different experiments, Camland, Gerda, Seor, and versions of it, and these are sort of the bounds that they have. It is thought that they will be able to come down through the inverted hierarchy, and if they do that, then of course we'll know which one of these hierarchies it is based on just neutrino-less double beta decay. I should say we'll know which one of the hierarchies it is, assuming that neutrinos are Majorana, right? We have to make that assumption to make this go. Okay. All right. Yeah.
Row 8 is a constraint from the double beta decay, right?
Yeah. These are up here is ruled out. Has been probed and not found.
So then what determines the shape of the yellow and white lever?
Right. So one of them, when you arrange to have the neutrinos in a particular pattern, and this is now you've pressed me on the exact, okay, pressed me on a detail, but if you do it in one particular pattern, then there's no way of getting a zero, in the sense that here we have these neutrino mixing matrices, and notice it's U squared, not U dagger U. So there are phases that sit here, and there can be the possibility that you put an appropriate phase in and it will vanish for the normal hierarchy, but not for the inverted hierarchy. And that just boils down to so in one of these hierarchies, I'm basically taking two of these masses and weighing them against two sets of combinations, and I have one light one, and then maybe I have a phase there, and the other one I'm doing the other way around.
What are the coefficients here? UE1, 2, 3?
Yeah, so these are the Pmns matrix coefficients of the mixings between electron to the mass eigenstates of 1, 2, 3.
So the region in yellow and white, they depend on the Pmns coefficients.
The yellow and white are the difference between whether you have a hierarchy that is, let me draw it, is two neutrinos here and one there, or one here, one there, one there.
So the exact shape of the curves, they depend on the coefficient.
And then you're right, and the exact shape of the curves then boils down to taking this hierarchy and putting in the mixings that we know, or the constraints that we know, given the mixings. The other one is the other one.
For which experiment can we constrain the Pmns coefficient?
Which experiments? Oh, it's all of the neutrino thing. So this is everything from atmospheric neutrino oscillations to solar to reactor, all of it. Yeah. Yeah.
Does that mean, you said there are zeros, so that means there's a range of neutrino masses where there's also no neutrinos that would be okay?
Yes, if you're in so-called normal hierarchy. Correct. That's life, okay? Just, I mean, so this is another one of these fundamental principles, which is, right, that this is a great idea for trying to probe which type of neutrino we have. And this is a fundamental property of our universe, right? What type of neutrinos we have. Yes, you could be unlucky and not be able to find it. And that's life. I mean, and if this is true, you'd have to do something else, right? You have to. Yeah.
So this matrix element in which you have, which determines neutrino-less double beta decay, it depends on quite a number of parameters. So one of these parameters are masses, which Ram was talking about. Other parameters are elements in Pmns matrix, which you can measure in neutrino oscillation experiments. But there are two extra parameters which can never ever be measured in neutrino oscillation experiments, which are called Majorana
phases. Yes.
And these Majorana phases appear there.
Yeah, good. Thank you.
Majorana phases indeed can be tuned in such a way that the effect goes there.
Yeah, very good. Yeah, and then that goes to counting the number of effective parameters that you have in either scenario. So if we had the Dirac case, we would count the number of parameters in the Pmns matrix as exactly the same as the CKM counting, namely that there's 3 real angles in one phase. That's the phase that everyone is trying to shoot everyone. That's the phase that Dune and T2K and these experiments are trying to measure. But if it's Majorana, there are more phases, and 2 more phases, and exactly as Misha pointed out, they enter here. Excuse me. Okay.
It's like the CP violation phases?
Yes. Yes. Sorry. Yeah. Yeah. Good.
So does it mean that for certain region, like for certain range of phases, there is no way for us to understand whether they have Majorana masses or like,
from this process.
But in general, you can still tell, like other experiments.
Well, now it gets complicated because now you're going to have to potentially hit a different flavor of lepton, and if you do that, you have to do a different process, and it's probably not. It's not a nuclear transition anymore. So it's something else. I don't know that. I'm not an expert on elaborate ways of trying to probe delta L equal to 2 processes other than this. I know of other different things, but yeah. So yeah, clearly you have to do more. Yeah. Okay.
This Majorana phases you cannot find experimentally.
Yep.
So the further process is
Yep. I mean, yeah. Up to some hypothetical.
maybe
Yeah.
today or maybe tomorrow.
Yeah. Yeah. Okay. Good. All right. That's the end of neutrinos. Why did I do it? Because I wanted to first make sure that everyone was on board with exactly what I mean by the standard model and exactly what I mean by extending the standard model. You now also know exactly what it means to have a higher dimensional operator and the fact that it generically breaks global symmetries of the standard model. It's already there. It doesn't have to, but it did in this case. Also, right, if I extend the matter content to include a right-handed neutrino in the all the way to as in a Dirac mass, then of course I've extended the content, and that's changing. That's going beyond the standard model. Okay. So, yes.
Can I make a comment?
Sure. Yeah.
Okay. It seems to me that the case in which you added right-handed neutrinos, one should add something. And so let me add this.
Yeah.
So if you introduce right-handed neutrinos in the game, Kribs was considering the case in which lepton number is still conserved.
Correct.
However, following to your logic,
Yep.
if I introduce right-handed neutrinos in the game,
Yep.
I should add to the theory all dimensional 4 operators, meaning that for this right-handed neutrinos, one must add extra terms which lead to Majorana masses of this right-handed neutrinos.
Correct. Right.
And if this is done, then the first case and the second case start to be equivalent.
Right. With the right. So let me. Yeah, that's great. I take the comment. It was a similar comment we're already getting here. So this is the point that how I realize getting this operator in the first place can be from adding a right-handed neutrino with a Majorana mass. The Majorana mass violates lepton number by 2 units. I integrate it out. And so here's my new right, and then I have H new left, or even L there. I integrate out this right-handed neutrino with a very heavy mass, and I will precisely generate this interaction, which is otherwise known as the seesaw mechanism. Okay. So yeah, that's absolutely true. If I violate lepton number by 2 units, then I will just generate this operator directly. Mm-hmm. Yeah, good. Okay.
So,
Yep.
if you give a lepton number to the right neutrino, do you still violate lepton number?
If I give a what?
A lepton number to the right neutrino.
If I give lepton, so the statement is that the way I would, once I add these fields at a high scale, they have their own global fermion number. Once I give them a Yukawa coupling, that links that fermion number to lepton number. So these become one of the same number. Okay, does that make sense? Yeah. And then it's only then after I integrate this field out and I generate, I drew it, of course, I meant this. It's only after I integrate this out and result in this dimension 5 interaction that I've written there, right, that this field is gone and I'm left with just the standard model plus this interaction.
The first diagram doesn't violate lepton number. Does it?
It does, because so this is, if I put chirality arrows in, it's this. This is a Majorana mass here. Sorry, yeah, right there. I have to do that, and in the case when it was Dirac, this was 0. And there was no lepton number, and then they survive all the way to, to arbitrarily low scales. Okay. I want to turn to sort of other aspects of technical unnaturalness. I already mentioned, of course, we have the CC problem, we have the Higgs mass squared, or the hierarchy problem. I mean, theta. There's another parameter that's technically unnatural. The quartet coupling of the standard model. So we're used to saying we take the Higgs mass squared to 0, there's no enhanced symmetry. But just for the same argument, I take the quartet coupling to 0, there's no enhanced symmetry. At first you'd say, well, fine, sure, but who cares? We know what this number is. We've measured it. It's 0.13 or so. When you write it suitably in the potential, right? It becomes precisely the Higgs mass. Lambda times v squared becomes the Higgs, the 125 GeV Higgs mass. I should be clear about what I mean. The scalar excitation above the minimum, little h. This becomes precisely the Higgs mass, so we've basically measured it. So, and it's, okay, maybe it's not 1, but it's order 1, so why do I care? But it's technically unnatural. And then you're like, okay, so what? That means that it's technically unnatural from the strict definition that as I send it to 0, there's no enhanced symmetry. And as a consequence, that means that there are other contributions that can enter to renormalize its size. And they're far from trivial, but they're essential to knowing the future of the universe. That's what I want to explain now. Okay. It's probably going to seem to some of you this may seem like sort of maybe a trivial or an aside point. But I actually claim that it's actually a critical point to understand. The first place you see it is in the future, is the long-term future of the universe. The second and subsequent places you see it is how you realize getting this coupling from any new physics scenario. Okay, so and in that way, that's why I think this is important to think about. Okay, the quartet coupling of the Higgs. It's lambda. So I might write this I'm already doing. And I'm being a little bit quick with this, but I'm imagining taking the entire doublet and just putting it together. So I'm in, if you like, I'm in the electroweak preserving part of the theory. So I'm at scales above V. So then if I look at the gradative corrections to this, they are, well, whatever I started with. That's the tree level piece. And then I start adding other corrections, and I certainly have things like this. I started to, yeah, all right. Okay, lambda squared, 16 pi squared, a log, and some number that's positive. And then I have interactions with fermions, where I now have y of the fermion to the 4th power, 16 pi squared, a log, okay? But critically, because it's a fermion loop, it's minus. The fact that this thing is what I just said, technically unnatural. There is no enhanced symmetry setting it to 0, is why precisely this coupling is not multiplicatively renormalized. I don't pull lambda all the way out of this equation. I have a y to the 4th sitting in front of my correction. So if I wish, I could write this as a renormalization group equation. This is exactly what you would actually do. You would never really write it this way, but I'm just being schematic. You would write the RGE, and the RGE would have a contribution proportional to this and to the fermions, and then higher orders.
Sorry, I'm still
Yeah.
very confused. So you would say that the fine structure constant in QED is technical unnatural.
Is natural. But this guy is not. If you send all couplings to 0, all H couplings, Yukawa couplings, and lambda to 0 simultaneously, then this operation is technically natural. Oh, sorry.
So you one, yeah. So you ones are strange, and that's worth a conversation. Yeah. Okay. I'd be delighted to talk about that. Not right now, but yeah. Okay. Good. So, but this is why there's no lambda sitting in front of here. Is the Tufts principle? Okay. That's why it's not there, and that has a consequence, because if I take lambda as a function of the renormalization group scale, and I run it up to a high scale, I find here's my 0.13. There's my value at 100 GeV, or thereabouts, the weak scale. And let's just, for reference, let's put 10 to the 18, the Planck scale there. It does this. Okay. And this is, oh, I should have emphasized, this is 0. So this is negative. The quartet coupling runs negative. It could only have done that if it were technically unnatural. Because if it were technically natural, it would be multiplicatively renormalized. Once I set it to one sign, it stays that sign. Okay? But the fact that it's not means it can go negative, and it does. It does. Yeah.
We don't know whether it does or it doesn't.
In the standard model, it does.
In the standard model, we don't know whether it does or it doesn't.
No, I would say in the standard model, we know it does.
No. This question is related to the Tokyo-Yukawa coupling.
Yes.
Okay? And Tokyo-Yukawa coupling, as it's found at LHC,
Yes.
within 1.5 sigma errors, allow the scalar coupling to be positive. And yes, you can say that there is 1.5 evidence for the scalar coupling to become negative at some scale, but you cannot say that we know for sure that it does.
Fair enough. I will say if you take the central values of the top quark and the Higgs mass, it runs negative.
Again, there is a non-trivial relationship between the Monte Carlo top mass as it measured at LHC and the Tokyo-Yukawa coupling, which has systematic uncertainties, which are so the correct statement is if you take the standard value for the top quarks, if you forget about the systematic uncertainties, yes, then it proceeds.
So I think I'll take this offline. I think it's best to do that. I will say that there's been a number of people who have done the studies of this. So I'm taking this from one particular study that they did RGEs to 3 loops and so forth, and they took into account the uncertainties in the top and in the Higgs. And I even went to and re-verified the Higgs they used versus the central value today. And with all of those numbers, it still runs negative. There is absolutely an uncertainty band that we can debate whether it hits 0, it's a little bit low, and how many sigma. Okay, I'm happy to admit that there is an uncertainty here where beyond which it could become positive. And then the only debate at that point is this 1 sigma, is it 3 sigma? Fine, yes, we can debate that offline. Great, okay. But the central value, it goes negative, I claim, or at least I should say my colleagues claim from their wonderful analysis that they did. I didn't actually do this calculation. I'm taking this from a reference. So the reference is 3 1307, 33536, which includes a whole number of authors. Okay, good.
There is another reference where people claim 1.56.
Okay. Nevertheless, it's still true. There's a negative sign, there's a yt to the fourth, and there's no lambda in front. Okay, that's all true. Okay, that's not going anywhere, and that all has the same principle is at work. So if you then look at what does this mean? So a quartet coupling that goes negative at some point suggests that if you go to large field values, that eventually the potential, the Higgs potential, well, you would think it would keep turning up. This is the parameter that was supposed to cause it to turn up. It will eventually turn over again. And there could be a new minimum away from the electroweak breaking minimum that we know and love. So if there's...
Can you say that again?
Since this is the coupling that is keeping the Higgs potential positive and is leading to the minimum that we know and love, the one that we're in, and we all have mass and so forth, masses that we know, if at large renormalization scale, which is equivalent to sort of, if you like, large field values in the Higgs potential at some level, then this negative value would suggest the potential is actually turning over. And so there would be a maybe new minimum. For example, if I extend the standard model to include a dimension 6 operator, that would then come in to fix the Higgs potential again. Right? That's the simplest way to sort of imagine this. So the negative means there could be, the universe could itself be unstable, and people have calculated that. And let me just show you what that looks like. And this is from this reference, okay? So here's the broad picture first. So here's the Higgs mass, here's the top quark, and just sort of for reference, here's 200, 200, 0, 0. It looks sort of like this, 100. Okay. That, and then, okay. And the statement is the region that is here is unstable, which is to say that if I turn this Higgs mass into a quartet coupling, I take this top mass, turn it into a top Yukawa coupling, and then I run it, it will go definitely negative, and I will definitely have the universe, okay, collapse. We happen to live right about there, which is within the so-called metastability, in that the universe lives for a long time. How long? Okay, now the uncertainties are very large because it depends very sensitively on both how you do the calculation, exactly how deep this goes. Okay, there's a whole number of uncertainties there, but we're talking about, 10 to the negative 1,000 probability that we will tunnel into this new universe. Something of that order, okay? Yeah, if you blow this region up, you find that here's the metastability region. And so this is stable down here. This is unstable. And at least at the time, the contours looked something like that. Okay, and again, we can debate whether it's 2, 3, 1 sigma, fine, yeah. Okay, but the point is, it's sort of these central values err a little bit into the metastability side, and so that's interesting. It's interesting from the point of view that we happen to live in this universe where we're very close to this boundary of being exactly stable, though not exactly there, and we seem to be close to having this quartet coupling run to 0 or, as I said, a little bit negative. And The fact that this is even potentially an issue is precisely because this coupling is not technically natural. That's the point, right? That's the whole point of this.
So, aren't you extending the standard model 16 orders of magnitude?
Oh yes, absolutely.
That's too much, no?
That's too much. I don't know. I don't know. What new physics do you know for sure that is entering?
No, I don't know what physics, but I would expect something.
Good. Yeah. So, yeah.
But if it's that extrapolation too big, that plot makes no sense, no? Or
Sure. Yeah. So if basically, I'll say it differently, right? I only need to just barely touch the Higgs sector in any very small way somewhere in here, and I can completely change this result. But importantly, right now, I could change the result on either side. There's nothing to tell me I can't add another even deeper negative contribution and then it makes all of this worse. Well, apparently I can't, because if I did, we'd be unstable and we wouldn't exist. So I guess anthropically we know there's not. But, all right. Okay. Yeah.
But the fact that we are living right on top of this very thin metastability region,
Yep.
does it maybe show or maybe reveal that there is no new physics up to 10 to the 12 GeV?
So you're saying you want to make something of lambda go to 0.
If there is no new physics, then we will leave this with this region,
Yep.
which is so thin.
Right. So.
The fact that we are on top of it, like it's triangular.
Right. So fine. So you're suggesting that I should make something of the place where lambda goes to 0, as in maybe that's where I should expect new physics to lie. I could even say it a little bit differently and say, perhaps the fact that this thing goes to 0 is interesting because maybe there is some new physics that renders this coupling technically natural again, and then it should take over here and go from there. In fact, there is physics that can do exactly that. It's a type of supersymmetry. Okay. It's something that I worked on 5 years ago, but it doesn't matter. So there's actually a type of supersymmetry that will come in that will predict the quartet couplings exactly vanishes there. It doesn't exactly vanish. It's a little bit positive. But anyway, okay, fine. So there it's different because now the nature of what it means to be a quartet coupling has changed from the effective theory of the standard model to a new theory, which has different properties.
Yeah, but if you want to solve the hierarchy problem, you have to introduce new physics at the TeV scale, and then you change the picture. No?
So the supersymmetry that I'm talking about would actually enter here or near about there, not down here.
Okay, but then you don't solve the hierarchy problem.
True. So it would only do something here. Yeah, that's right. So it's a split type of
Is there a
supersymmetry.
hierarchy problem itself? Either we live in the metastability region, but not both at the same time.
No, so I'm treating these as different in the sense that the hierarchy problem is precisely why is the weak scale stable against radiative corrections from heavier scales.
But for this, you need to introduce new physics at the TeV scales, and then you change the running of lambda, and you leave the metastability region.
Yes, that's right. So if I really solve the hierarchy problem, then I'm presumably completely changing this curve. Yes, I agree with that. I completely agree with that. This is all standard model. Yeah, I said it. I'll say it again. It's all standard model. Okay, but it's so that. Again, if you're really worried about your existence suddenly going into nothing very soon, okay, if that is your fundamental fear, I don't really believe this is the story, because I really think probably something else is coming in somewhere in here. For example, it's the top quark Yukawa coupling that dominates this, but no one really believes that all of the Yukawa couplings are simply set by Planck's slop. Okay, there presumably is some mechanism that's actually ultimately setting all of these things there, and that's, again, presumably at some lower scale. Those are admittedly judgment calls. Those are opinions, not physics statements. But if you do that, then you begin to think that, okay, it's probably not critical. Yes?
I never understood the transition from this observation on the running of lambda,
Yes.
and then going to this kind of phase diagram there. I would have thought that in the meaning of this curve that lambda is mu dependent means the scattering of the Higgs against the Higgs depends on the center of mass energy. This is usually what it means that the coupling is running.
Yes?
But why does the structure of the vacuum depend on lambda at very high scales?
so it's what I am doing is effectively treating the renormalization scale as equivalent to as if I were to go to very large field values in the potential. And to go to sort of large field values is akin to going to large renormalization scale. And in that connection, in that process, that's where then I would run into this difficulty. So if I
high field intensity somehow.
But because in the lab you have Vev over renormalization scale mu.
Right.
Vev over mu, you want to keep it under 1, otherwise the lab becomes divergent.
So this term is here. This is the way you would write it in, not in a MS bar scheme, but in some on-shell scheme, and at some level that you can sort of think of it as, right, trying to construct what is this coupling. All right. Anyway, where am I on time? Yeah, that's what I thought. Okay, good. All right. I think I will, since I'm 3:30, right? 3:30 is the time. Yeah. All right. So I think I'll stop here, and then what we'll pick up tomorrow is discussing. Now that we've understood a little bit about technical unnaturalness in one context, then I want to tell you more about technical unnaturalness in this context.